So we're happy to host today for the first talk of this semester Gilad Karpel from the Technion. He's a master's student advised by one Meir and Subri.
Yeah.
His research is all things continual, reinforcement, continual learning, anything that's moving. And thank you for coming.
Yeah, so I will start talking about our research, which is namely optimal implicit regularization in i-dimensional continual linear regression, which will be presented by me. We'll mainly speak about two papers. The first one is the optimal regularization in i-dimensional continual linear regression, which was accepted and presented in the previous ALT conference. And the second one, optimal implicit regularization in i-dimensional continual linear regression, which was recently submitted. So for those of you who are not familiar, we'll start with a kind of bit of introduction after the introduction that we have about continual learning. So unlike standard learning, where you're given the data set X and the labels Y, and you kind of expect to learn a model such that given the data, you can accurately predict the labels. In continual learning, you don't observe all data simultaneously. You get it sequentially over T sequential tasks. Each task is characterized by its own data set and labels. And at each iteration, you can update your predictor by fitting only on the current task without having any access to samples from previous tasks. So naturally, one of the main problems that the memory has in such setting is known as catastrophic forgetting. And this problem actually led to the motivation of the entire field of the continual learning. So what is catastrophic forgetting? Adaptation to new task leads to a degrade performance over previous learned tasks. So let's, for instance, look at this figure. Upon learning the first task, the predictor can accurately predict the labels, those in orange and those in blue. And then there was some change in the distribution of the data. And the predictor kind of overfitted the second task. And thus, it led to a significant degradation over the performance in the first task, while in the ideal case, we would expect to learn a model that can accurately predict both tasks simultaneously. And indeed, here the solution is feasible. So this is the ideal case, what we strive to eventually get. So just to be on the same page, I will show you the general scheme that continual learning systems must follow. Each task, you get the data set and labels corresponding to the specific task. Then you update your parameters according to some learning rule that can only have access to the current data and the previous predictor. And then you output your final predictor. So back to our main question, how do we mitigate catastrophic forgetting? And this is the main question in continual learning, of course. So there's been proposed like many empirical works that aim to reduce catastrophic forgetting, but they kind of can be split into three main fields. The first one is the replay methods, in which you aim to memorize specific samples from each one of the tasks. Then you output your final predictor based on these samples. In regularization-based method, what you do is to regularize towards the last predictor. This way you don't entirely forget about previously learned tasks. So it makes sense to use regularization-based methods. In parameter isolation methods, for instance, you allocate specific parameters for each one of the tasks. They generally require to know the task ID. Then you freeze all other parameters and you learn only on those allocated parameters. So replay methods, naturally, one of the main problems in replay methods is the memory constraints. You can't memorize too much, especially when you have many tasks. In parameter isolation methods, you need to know task ID, which is not something that is always known. But it makes sense to use it like in seasonal cases, like kind of predicting for each season the right predictor. So we will focus on this field, the regularization-based methods. So let's start. So we first studied the first scheme, which will talk about the continual linear regression with delta regularization, in which we aim to minimize the mean squared error plus some regularization towards the last iteration. So while this idea may look very simple, since the entire regularization is governed by a single parameter, which is lambda, recent empirical works found that it works very well to standard baselines in continual learning, which is kind of surprising, right? So we ask ourselves, one of the most natural question would be, what is the optimal regularization strength? And if we can't answer this, if it is too hard question, then how does it scale with the number of tasks? So even knowing how it scales with the number of tasks would significantly help us, because we can find the correct scaling over shorter task horizons, then adapt the same scaling over longer task horizons.
Do we have a hope to have an answer for this question that doesn't use any assumption about the relation between, because I can, like, on one hand it can be that all tasks are very similar to each other, in which case the optimal lambda should be very high, and on the other hand I can assume they're like completely different, and so do we even have a hope that there is an optimal lambda with no assumptions on the
data
relation between the tasks?
So that's a very interesting question. Actually, it very much depends on the teachers, and we will show two general schemes of the teachers in which the optimal regularization strength really differs. So the second studied algorithm will be the implicit regularization. Actually, there is a very good reason it's called the implicit regularization. So what about cheaper alternatives? What do I mean by cheaper alternatives? Let's go back to the first scheme. So in order to explicitly solve this, you need to solve the least squares problem, which requires taking the inverse of a big matrix over t sequential tasks, which is not something that is also always feasible. And you also can consider taking gradient descent or stochastic gradient descent until convergence, which might make more sense computationally. However, our analysis finds that you have to have many gradient steps in order to explicitly solve it and to see the exact phenomena that we identify in the paper.
Can you repeat that again? I mean, what's the...
So instead of solving this explicitly and taking the inverse of the matrix, you could do gradient descent or stochastic gradient descent until convergence of this objective. So what instead we do here, we take finite number of steps of gradient descent, each one of the tasks, and then we output our final predictor. So main question for this case would be, is there some relation between this implicit regularization and the explicit regularization, the L2 isotropic regularization? What is the optimal choice of the number of steps and the step size? How does it scale with the number of tasks? Once again, if we can't answer the first question, the second question would be very informative. Is it cheaper? If it is cheaper, then how close the generalization loss in this case will be to the explicit regularization?
Regularization here is not on the W anymore, unlike the previous one?
No, so there is no regularization here at all.
Right.
It's called implicit regularization. So it induces a regularization. We will speak about how it specifically induces regularization, in what sense, but there is a close relation between this scheme and the first one. And the third one is the generalized L2 regularization. So what about more general schemes? What do I mean by more general schemes? So instead of taking regularization based on a single parameter, you could do to any PSD matrix, positive semi-definite matrix. However, empirical works generally use diagonal regularization matrices due to memory constraints and computation constraints. And this is actually what we also do here in our paper. So this already covers a significant algorithm that are used in practice. Actually, most of these citations indeed use diagonal regularization metrics, and of course generalizes the compact L2 regularization that I mentioned earlier using MT equals D over N times lambda identity. So of course the main question will be how to optimally tune those matrices, and I will aim to show you that it's not only a hard question but also impossible in the general case. So we want to draw some conclusions. So when does this explicit regularization still remains optimal across all the diagonal regularization matrices? So this will be an interesting question because our analysis showed that we can find the optimal regularization strength under some assumptions. So identifying when it remains optimal would be very informative to us. So I won't speak much about prior work, but I do mention them. They mostly analyze worst case bounds, followed by a great line of work by Avron, and a few other works that were accepted to highly respected venues. However, most of them lack empirical evidence and they couldn't apply a practical rule of thumb. They need to make a stricter assumption about the labels. So what do I mean by stricter assumption? They assume that all tasks are simultaneously realizable, and it means that there exists a single teacher that solves all tasks without having any noise. And in most cases, it can accommodate any arbitrary data. It doesn't need to make any statistical design, as we assume here. You will see what we assume here. So let's talk about the statistical setting. It will be simplified, a bit simplified. However, I want you to imagine this very big matrix with the dimensions of n. N is the number of samples, and d is the dimension. N and d are both going to infinity while they remain comparable. So n over d goes to some alpha. Actually, in the first walk, we assume that alpha is less or equal to 1. That is we are in the overparameterized regime. However, each one of the entries in the matrix has i.i.d entries with mean 0 and variance v of x. And we have the labels are generated from a noisy linear model that is yt equals to xt times the teacher plus noise. The noise has the expected value of 0 and the isotropic covariance matrix. Isotropic covariance is a constant times identity. We focus on generalization loss, which is defined as the average loss after observing the sequential task.
The W star T?
No, it's WT. Where?
No, the W star T.
Yeah.
What do we assume about them at this point?
You assume it only exists. At this point, they can be any arbitrary. Yeah. So let's talk a bit more about the generalization loss, since I didn't tell you how we explicitly choose those loss functions. So it would make sense to choose the loss function to be the mean squared error, right? We assume a noisy linear model over the labels. And indeed, some theoretical works, they explicitly use the mean squared error and they aim to minimize this loss. However, under our statistical model, averaging over random test data and labels noise gives us this identity. And it is readily seen that averaging over the mean squared error is equivalent to minimizing the distance of the predictor from the teacher. Right, so using the definition of the expected generalization loss, the generalization loss can be defined as the average distance of the last predictor from all the teachers.
This is because you assume
The isotropic label noise.
Data,
Yeah.
Right? So you sort of save the need for the Malanobis norm thing.
Yeah.
X transpose X is equal to I.
Yeah, so it's
No, x transpose x is not equal to I.
no the expected X transpose.
Expect, yeah.
Yeah, that's why you're so that's a really
So first theorem provides the exact generalization analysis. So it looks like this. Not that pretty, but also the dependence on A, B, and C on the problem parameters is obscured here. I didn't show you because the dependence is very non-trivial, but I wanted to show you the complexity of the problem and how it very much depends on the teacher setup. So we show you the proof idea. We start with the solution for a specific task T. Right, solving the least squares will deal this quantity. And then we denote P of T equals to this matrix, and ST to K is the multiplication of PT until PK. Then unrolling this identity will deal us this identity, and then I will just remind you that the expected generalization loss will be defined as the average over the distance of the last predictor over all teachers. Then we simply need to take the norm squared over this entire term, but we need to understand what is the expected value of those matrices, right? For instance, say you took the norm squared over this entire term, you look at the first term, then you have W0 minus W1 star transpose ST21 transpose ST21 W0 minus W1 star. So you want to understand how is the expected value of ST1 transpose ST21. So for that we invoke the Marchenko postulo. Don't worry, I will tell you what is the Marchenko postulo. The Marchenko postulo So assume you have the very same matrix as we assumed in the statistical design. You have those dimensions that are both going to infinity while they're mean comparable. Then under the Marchenko-Pastulo, we define the Graham matrix, which is 1 over n x times 6. Then the empirical spectral distribution of this matrix converges weakly to a Marchenko-Pastulo distribution with the parameter of alpha, in which we define the CDF to count the number of eigenvalues that are less or equal than x. And this converges weakly to the integral from minus infinity to x of the PDF. And the PDF is in very nice compact form, by the Marchenko-Pastulo, with alpha plus minus equals to this. And if alpha is less than 1, then the Graham matrix is not invertible, so we must have additional point mass of size 1 minus alpha at 0.
Just making sure this is specifically for x's that are samples from Gaussians, right? It's not
No Gaussian. i.i.d.
i.i.d. regardless of what is the distribution pair coordinate?
Yeah.
Like a CLT kind of thing?
Not exactly. The proof is not exactly the CLT. But
every element of W is assigned.
So
you're correct.
W becomes CLT.
The correct intuition would be CLT. I agree with that. But the proof of the MP law, as I remember it, doesn't explicitly use the CLT. But I agree, this is a nice situation.
And this is only asymptotic. It doesn't have convergence rate or something.
It does have. So for finite n and d, I will talk about the specific resolvent of interest, and those indeed have up to, for finite n and d, you have the asymptotic. So note that by the Marchenko-Pastulo, the entire spectrum lies between alpha minus and alpha plus. Right, this is something that we will later use. So I want to introduce you the idea of the resolvent matrix. So again, we assume the very same matrix in which the dimensions both go to infinity, while the ratio remains comparable. And we have also finite for plus epsilon moment for some epsilon greater than 0. It doesn't matter which epsilon. So the resolvent matrix will be defined in this way, normalized by the feature variance. The feature variance is the variance of each one of the entries. So it can be shown to converge to a scalar times identity, almost surely. And since it converges specifically to a scalar times identity, it makes the analysis way more tractable. And from now on, the analysis will be much simplified than the analysis than the identity that we saw earlier. Right, so the expression for the expected value pt squared, and this expression that naturally appear in our analysis will become identity times scalar. Now we can draw some conclusions using the explicit expression for the expected generalization. So, but first we need to assume a special case relating to your question. We need to assume a multiple i.i.d. teachers, and we will later see why we need to assume the multiple i.i.d. teachers. So our assumption would be that the teachers are i.i.d. are distributed from some distribution independently with mean W star and covariance matrix of sigma, independently of all random variables. But we know that this assumption can be generalized to perhaps teachers that roam independently from some distribution. The sum distribution must have common mean W star and the same covariance matrix sigma. So it doesn't have to be the same distribution, just simply the same first and second movement. So in this case, the generalization loss can be reduced to a very nice compact form. It's not actually that very nice, but
It's not very compact.
yeah.
Other than that.
Yeah, and also A, B, and C are very dependent very non-trivially on the parameters. It's not very nice, but it doesn't depend on the teacher model. So this is the nice thing about this expression. And we can draw some conclusions using this very expression. So our first lemma says that in the i.i.d. teacher case, if you employ the first scheme, the explicit regularization with some label noise which is greater than 0, then if you have a single teacher, right, W1 star equals to WT star equals to WT star, then the generalization loss will decrease with the number of tasks if you use the optimal regularization strength. And the second part states that if trace sigma greater than 0, that is, there exists some variability between the teachers, then for any fixed lambda greater than 0, the generalization loss increases as function of t, starting from some t, starting from some threshold. So if you add more tasks, you could generalize better. That's what the first part says. And if you use more tasks for any fixed regularization strength, the generalization loss will increase.
So just trying to sort what this means. Okay, so the first problem is this is not really a continual learning. You just didn't know it's not continual learning, but you happen to live in a world where you keep getting more and more samples from the same distribution, right? And had you known, you would have just learned. And so let's say somewhat you knew a priori that it's going to be the same one. You knew a priori that there's only a single teacher. Then would you be able to choose a better lambda? But still, you have like bounded memory, so you can't save all the data from the history. Is there?
So we try to make a practical rule of thumb in order to choose the lambda, the optimal lambda. You can know a priori the optimal lambda star as function of t, right? So it very much depends on the data, on the teacher setup.
I know. Let's say I tell like it's the simplest world. I told you there's a single teacher.
You knew the single teacher?
You knew it's a single teacher.
Yeah, so you could optimize over the generalization loss. Yeah.
And then we know what that lambda will be.
If you know the exact problem parameters, which is d of x, the feature noise, the label noise, and the aspect ratio is n over d.
Okay.
And you knew that both are, if the entire assumptions are satisfied, then of course
you understand how much are you losing by the fact that there are unknowns and what are the unknowns. So first of all, you say the algorithm didn't know a priori that it's a single teacher. Okay, I believe we will lose something from it. And you say there are a few more. It didn't know the variance and things like that.
Yeah. And you also don't know that n and d are both going to infinity. But actually, our empirical analysis shows that even when n and d are finite and even pretty small, then we could recover our analysis. You will later.
And for the second one, what happens if we flip the order of the quantifiers? So you say for any lambda, there is a t where things will go wrong.
Actually,
also for any t, there is a lambda that you can get what best or something.
Yeah, actually, I think that this theorem can also include this case, the single teacher case. I'm pretty confident. So back to our main question: what is the optimal regularization strength? So we find that it scales as t over lambda t over all regularization strength that are greater than 0. Or more specifically, for all epsilon greater than 0, there exists some threshold, which is symptotically O of 1 over epsilon squared, such that for all t greater than threshold, then lambda star is some scalar up to some epsilon accuracy. Back to your question of the problem parameters. Furthermore, in the noiseless single teacher case, which is v of z and trace sigma both simultaneously 0, then it holds that lambda star goes to 0. Right? It's undefined whenever trace sigma and v of z simultaneously 0.
Goes as t goes to infinity. No, what is underneath the arrow?
What is
lambda star goes to 0 as 1 goes to infinity.
No. Okay, I got it. So the optimal choice would be sufficiently small lambda. So we can't really use lambda equals to 0 because
I see.
Yeah, it wouldn't be invertible, right? In the general case, actually, it would necessarily not be invertible since we're in the overparameterized regime.
So now you're going to use lambda just like as a ridge regression kind of thing, not because it's continual learning, just because we need to choose among many identical. Many feasible.
We will see this in the experimental setup and what our real analysis says in the experimental setup. How does it come to empirical setting? So how good does it get? So if t goes to infinity, if we had an infinite task horizon, then wt goes to w star. and this achievable whenever lambda goes to infinity. Right, W star will be the global minimizer. W star is the one that we strive to get. If you had infinite task horizon, then you could get W star. Not necessarily get, but be close to it. So we find that as t goes to infinity, the generalization loss will decrease as function of lambda. And as lambdas go to infinity, the iterates converge to the global teacher. So you first take the limit of t to infinity, then you take the limit of lambda to infinity. So imagine you had the infinite task horizon, you ran it with some lambda, then you took the limit of lambda to infinity, and the expected distance of Wt from W star will go to 0. So we start with empirical validation over synthetic data. Each one of the entries is distributed as a standard normal distribution, 0, 1, with pretty small dimensions, right? We assume that n and d are both going to infinity, but here there's pretty small dimensions, and I would like to show you that our theoretical analysis can still be recovered when n and d are pretty small. So we first find that the regularization can decrease the label noise floor, and it takes more time to decrease to the optimal generalization loss. Yeah, it makes sense because lambda star's case is t over lambda t. If you used higher regularization, you would expect the convergence to take more time. And also we find that the optimal regularization strength goes as predicted by the theorem. The optimal regularization strength is the middle point of the, right, it had some to epsilon accuracy. So what we did is to use the middle point. So let's go to the real experimental setup. So we consider MNIST-based data in which labels of 0 to 4 are converted to class of 0 and 5 to 9 are converted to class of 1. We consider two models. The first one is the linear model. The second one is the neural networks. We train with mean squared error, and then we report and test with 0, 1 loss. We consider two types of teachers. The first one is a single noiseless one, and the second one is the multiple i.i.d. teachers. Just a note about this. In the linear case, we take a subset over all MNIST data, and then we get the fitted linear teacher. And in the i.i.d. teacher case, what you do is to take each one of the entries and you put there some Gaussian perturbation. In the neural network case, a single noiseless will be considered one that was trained over the entire MNIST data. We consider two-layer ReLU network. So it was fitted until convergence, and the multiple i.i.d. teacher case, you would take each one of the parameters and employ there some Gaussian perturbation. So noisy labels are implemented as each label is flipped with probability of 0.2. So it very much differs from our real assumptions over the data. And we see that we have some near linear scanning of lambda star in the task horizon. The star here marks the minima, and the t grows in exponential rate, and also lambda star grows at the same rate. And seems to also hold in a neural networks model. And for those of you who may ask, what about the t over lambda t scaling? This is something that we will see right now.
What's the difference between the graphs?
So this one was trained on the neural network setting, single teacher, multiple i.i.d. teachers.
Okay.
This is the linear. Yeah. So here we considered, again, the linear experiments using a single teacher, and we find that there is an exact multiplicative mismatch between the one we predicted and the one stated by the theorem. So it makes sense, right? MNIST doesn't have isotropic covariance metrics, so we wouldn't expect to see exact matching. But once you consider a widening step, then you could recover the exact regularization strength as predicted by theorem. So if you had the entire covariance matrix, what you could do is a widening step to each one of the tasks, and then you would recover the optimal regularization strength as predicted by theorem. Actually, all of our analysis in the paper can be recovered if you had the real covariance matrix.
So when you say whitening, you mean just rescaling and shifting the mean, or
No,
general?
general, yeah.
So what if you do just the more basic, which is like a
No,
more
you
reasonable
couldn't
assumption?
recover the analysis. No.
But how big is the
Actually, we do it
gain you
here.
get from just or this is something you already did in the basic experiment?
Here, I think that in this plot we actually did it. We took the we did the standard normalization. Yeah.
For the entire data set before you started.
Yeah. For this plot, yeah.
Depends on variance. How
Yeah,
far
yeah.
away you might
It
get.
very much
No,
depends.
so I was trying to understand how much is just the basic version and how
Yeah,
much is
well, it could be
the off
arbitrary.
diagonal.
I'm saying it could be arbitrarily bad if the matrix is not diagonal.
Yeah.
in the original
And
basis.
this is what happens in the general case. But our main contribution in this paper is the scaling, which we find to also empirically. So while we can't really tell what happens in the non-isotropic case, we find that there is a near linear scaling in the aspect ratio as we predicted by the theorem.
So can you go back to the graph just so I one
This
before
one?
this, no, before this. The main prediction is that you have this. It lies on a line. The number of tasks.
The main what?
The figure that you're saying that there's a very good match is that the stars.
No, this one.
Oh,
We have
okay.
exact matching.
But the fact that it's a line, a straight line in log space, I guess.
Yeah. It is T over ln T. It is close to linear.
Oh, T over log T. Okay.
Yeah.
And where does the T over log T come from? That's from your main theorem.
Yeah.
Can you go back? Sorry. Okay.
No. Also, thank you for going back to this presentation. To the slide. The norm of W star is not something that we know, because if we knew W star, we could solve it perfectly. But the dependence of the in the norm of W star is logarithmic. Yeah.
And it probably decays relative to t, so
Yeah.
it's fixed and t is going to
Yeah. So it's not something that is very much significant. So initially we had this very general expression which was very dependent on the teacher setup, right? So it could accommodate any teacher setup, but we had to make the simplified analysis of the i.i.d. teacher case. So what happens if we don't assume the i.i.d. teacher? So I want to present you a simple counterexample to the scaling that we found. So we assume a sinusoidal model over the teachers, that is the teacher equals to a plus sinus of 2 pi fi times b, where a and b are vectors, and f is some frequency. First, we need to understand is the generalization loss as we defined earlier is valid here. So you see, the generalization loss as we defined earlier was averaging over all previous tasks. So would it make sense when you consider a sinusoidal model to take the average over all previously seen tasks? Well, the answer is no. What we do is to take a subset which are the teachers that share the same characteristics. So basically the same teachers. So what we do is to take the average over only these teachers. And we find that under our assumption, the generalization loss can, as we define, can be asymptotically oscillatory. So what we do is to analyze the worst case generalization loss. So what is the optimal generalization strength in this case? Then we find that the expected generalization loss, the infinite generalization loss, can be written as a very compact form. C0 plus square root of C1 squared plus C2 squared times the supremum over the cosinus of some expression. But when f is irrational, then there is actually one paper that showed that the supremum over the cosinus is 1. But the dependence of C0, C1, C2, and phi on the problem parameters is actually very non-trivial. We can't really solve this. We can't really find the optimal organization strength. So what we do is to verify empirically. So we see that lambda star is finite in regions where the frequency and the alpha are both between 0 and 1, and the alpha is also between 0 and 1. So in order to better understand this graph, maybe you should look at some special cases. So a special case will be f equals to 0, often 1. What happens in this case? Sinus 2 pi fi, it becomes a single teacher case, right? It becomes a single teacher, wi star equals to a. Then we found that in the single teacher case, lambda star scales as t over lambda t, right? So it is kind of a sanity check because we expect to get lambda star goes to infinity in those cases. And also an interesting regime would be to find that whenever alpha goes to 1, then the lambda star decreases. And why is that? Because whenever alpha goes to 0, the current task holds only limited information about the current task, so it would make sense to use higher regularization string. So as I explained before,
sorry, question about this. So there is maybe another natural variant of this question is, let's say I tell you that there is a finite number of teachers unknown. Maybe you know that they were sampled from some distribution, and you know that every task is first we sample i.i.d. a index, like which teacher, and then a sample. So you do, because what did your frequency thing achieve? It said like basically I'm iterating over the same set.
Yeah, over the same teachers.
But and there was even like a phenomenon that it was going in circles. But let's say you didn't know it's i.i.d. So but you do know it's finite. And let's say I told you how many teachers.
It's not i.i.d. here.
No, I'm saying, let's say I'm telling you there is a finite number of teachers, and each step is sampled from one of them. So there's no cyclic style of
Okay,
phenomenon.
got it. Okay.
Like, and even let's say you knew the number of teachers. You know there are 20 teachers. You don't know every iteration for which one of them is. Like, do you have a sense of like where would it map us between this? Like, it's almost like a single teacher because okay, I need to learn 20 tasks when I'm done, or is it closer to the i.i.d. or so what kind of complexity does
just to be on the same page, you have 20 teachers, which are what?
Let's say they were sampled.
Some deterministic teachers?
They were sampled from, so the full story is first 20 teachers are sampled from some distribution. Let's say the distribution.
So you have a prior which has 20. You want to understand if the prior of the i.i.d. teachers holds, right? This is what you mean?
But since you know there are only 20, so now you can naturally should have a higher lambda, I would assume, because you know it's not like in the i.i.d. case, you really don't try to learn from the past much. Just know that there's a distribution. But here we know there are only 20. I'm trying to get a sense of what happened here because it seems like here with the frequency, you do two things simultaneously. One is that there is some kind of structure. We're no longer in like, well, there are all sorts of teachers. You for some frequencies you enforce that there's just a finite number of teachers, and also you have that.
No, here you don't have finite number of teachers.
If the frequency
here
if the frequency is
I got it.
Constant over t.
Okay, yeah.
Those are these peaks, probably.
Yeah.
So I wonder what happens if you add that assumption, but without this cyclic thing.
So you have i.i.d. teachers, but if you have some frequency, then you must have cyclic.
So I'm saying I'm trying to add the. Okay, maybe I'm just.
Maybe we should talk about this later. Yeah. So as promised before, we would like to speak about the close relation between the first scheme and the second one, which is the subgradient descent and the isotropic regularization. And it will be very informal in this slide, and the next slide will be much more formal. But it just to give you the intuition into how we need to choose the number of steps and the step size in order to match this one of the bridge of the first scheme. So in which you end up with a matrix of this form, and in early subgradient descent, you end up with the matrix of this form. So what you essentially want to do is to minimize the distance between the two matrices, let's say in the spectral norm. So let's denote the SVD of the 1 over n x x, and by some algebraic simplification, you get this. So let's define f of mu, which corresponds to the quantity here, 1 minus gamma mu to the power of n minus lambda mu plus lambda to the minus 1. So how gamma and then should be chosen in order to minimize this f of mu for all mu? Just a quick reminder here that mu is bounded by the Marchico postulo, right? We said that before that the eigenvalues are bounded between alpha minus and alpha plus. So mu are in a compact set. Sorry. So the optimal choice will be n gamma equals to 1 over lambda. And why is that? We find this by a Taylor approximation that the leading terms cancel whenever n gamma mu equals to mu over lambda. So n gamma equals to 1 over lambda. And then you get the f of mu is mostly O over 1 over lambda squared, right? Once you choose n gamma equals 1 over lambda and you know that mu is bounded, it's in a compact set. So this will be very more formal from the previous one. So once you choose n equals to 1 over gamma lambda, each one of the tasks, then for large enough lambda, you get that the iterate produced by the early subgradient descent, the ridge, match up to O of 1 over lambda squared, and the expected generalization loss will match up to O of 1 over lambda.
This result has anything to do with continual learning, or is
Yeah,
it
it is.
general info? What?
No, it is also correct in a single task. Yeah.
Yeah, it's like a property of how early stopping approximates
Yeah,
regression in linear regression.
It is actually I'm pretty sure that it is actually true for all the spectral that all of if the spectrum is bounded, then this theorem is true.
And there's a lot of work in classical regression about the relation between ridge and stopping.
Yeah, they don't recover this exact analysis since they accommodate any arbitrary data. There is actually one work that shows that there is a constant relation between the gradient descent and the early stop gradient descent. Like they didn't show that it goes to 0.
Classical.
So there is one by Ali et al. From a paper from 2017. So yeah, this is one that I'm speaking about. I can show you later.
So basically, you're saying if I do gradient descent with early stopping on a linear regression problem, there is some relation to ridge. And what you're saying, if I have stronger assumptions on some of the parameters of the problem, I can have a tighter connection. And since in your setting you have this stronger.
Yeah. So it doesn't hold in all settings, of course. Yeah. Also, this upper bound can be a better upper bound if we assume like the i.i.d teacher case, for instance. We will see it. So we provide the exact generalization analysis for the implicit regularization once again. So we find that it is very similar to the one we got from the explicit regularization, up to changing those constants from A, B, and C to A tag, B tag, and C tag. It makes sense that the relation between tasks is still preserved, right? So the analysis is very. We would expect it to look very similar. So what is the optimal scaling in this case? So we find that gamma star is ln t over nt, and it makes sense, right? Since you need to choose lambda equals 1 over gamma n, so gamma equals to 1 over n lambda. So expect to see the inverse times 1 over n. But the proof is not that simple. It's not simply from the relation between ridge and the gradient descent. But so as before, for all epsilon gradient 0, there is some threshold, which is asymptotically O of 1 over epsilon squared, in which gamma star is a scalar up to some epsilon accuracy. Actually, here epsilon is in the numerator. Yeah, but it's practically the same thing. In the noisy single teacher case, then here gamma star any gamma which is between 0 and this value. What is this value? This value is 2 lambda max to the power of -1. This one get to the convergence of the gradient descent. And what is exactly this value? This value is the alpha plus we saw earlier in the Marchenko-Pastulo, right? The entire spectrum lies between alpha minus and alpha plus. So lambda max will be the alpha plus as we discussed earlier, and n goes to infinity, which is equivalent to lambda star goes to 0. So this generalization loss matches this of the one from the ridge up to O of 1 over T factor, which is slightly better than the one we got earlier, since 1 over lambda in this regime, lambda T over T, gets here another lambda T. So we first do empirical validation using synthetic data as before. We use the same dimensions, which are pretty small dimensions. We fix the number of steps to be equal to 20. We find that early step gradient descent and ridge coincide under a high enough regularization strength, as we predicted, and the optimal step size grows as predicted by the theorem. I don't have much more to say here. So the experimental setup, I won't go through it once again, since it's very similar for the first one. But here, instead of testing with 0-1 loss, we test with mean squared error, and instead of a bit flip, we consider Gaussian perturbation over the layers. And why is that? It more adapts to our statistical analysis, and we see that we have even better results than the one we got in the case of the label flip. So the black line here denotes a fitted lambda T over T scaling, and we can see that the exact scaling also holds in a neural networks model, and even in the multiple i.i.d. teachers case, right, up to the hero bar.
You should choose a different color, not black. It's very hard to see black.
Yeah. Maybe in the camera already.
Or make it interesting.
And error bars with stars is also somewhat confusing if it's a camera glare.
Yeah.
Oh, yeah.
We didn't have enough time for the submission. So as promised before, in the first scheme, we said that it is too expensive, right? We could employ gradient descent or stochastic gradient descent until convergence instead of taking the inverse of the matrix. But our empirical analysis shows that you have to take many gradient descent steps, and you see the scalings of T over lambda T actually very, very, very late, right? So you have to take 150 steps in order to start seeing it around task horizons, which is 600 approximately. While in this case, we see that the scaling of the lambda T over T holds from 2 to the power of 8 or even earlier, 2 to the power of 7, which is around 128, right? And here we use the number of gradient steps only to be 10. And actually, we could choose the number of gradient steps, descent steps to be even 1, and we would get the same result.
So in the linear case, there's something that seems more clear. I'm not sure if it appears in the neural network or it's just like an illusion, but like sort of a phase transition at some point. I'm talking not so much about the stars and the line, but about the shades, right? Like the MSE loss. What happens, right? So it seems like up to a certain T, the large MSE loss will occur when your gamma is too low. And then from a certain, like nearly a threshold, the big danger is if it's too high.
Yeah,
right?
yeah, of course, it makes sense, right?
So my question is this the same thing also in the neural network? It's not that clear. So there's always a phenomenon, and there's always a threshold, which is a function of T that tells me what is the point where the dangerous lambda will flip from too high to too low.
No, in the neural network case, we can't really say anything.
No, I'm saying what you see. I'm asking. It's an empirical question.
So
like that, you always have this kind of phase transition.
Not entirely sure that we had this all the time, but we ran it one time and then we put it in
The
the.
neural network is what?
It's two-value layer
Fully
network.
connected.
Yeah, fully connected. The simplest one. Yeah.
Simple enough to still look
Yeah.
similar to that.
But even a two-layer value network can. There is a theorem from the approximation theory that states that when the width go to infinity, then you can solve. Yeah.
One layer.
It's your,
What do you mean?
Yeah.
Two layer? One hidden layer
yeah. One.
or two hidden
No.
layers?
I think it was one hidden layer.
To make it wide.
So now that we are done with the second scheme, let's go back to the third scheme, which talks about the more general schemes, about the L2 regularization matrices, which are diagonal. So there exists extensions for the Marchenko-Pastur theorem that are about the non-isotropic covariance metric case. So let x equals to c to the power of half times z, where z has i.i.d entries with mean 0 and the unit variance. And in our case, c will be the covariance matrix. And we assume the very same things. We don't need to assume something additionally. So S and P are going to infinity. They remain comparable as before. We define the result matrix. And here we find that the result matrix doesn't converge to a scalar times identity, right? We wouldn't expect it to converge to a scalar times identity. But the fact that it doesn't converge to a scalar times identity makes the analysis way more non-tractable, right? We need to use the theorem that was developed actually on a very recent paper in order to have our analysis. So it's very not trivial, the fact that it doesn't converge to a scalar times identity. And also here, MP tilde is some scalar which solves this equation. Once again, very non-trivial, but it can be solved numerically. So just for simplicity, we need to assume here that we're in the single teacher case. Our analysis can be extended to the case of arbitrary linear teachers, even in this case. However, just to a bit more simplify, we assume a single teacher. Then this is the expected generalization loss in the case of generalized the diagonal regularization matrix. Actually, it's not very informative. I'm not trying to have some intuition about this expression, but I wanted to show you why this is impossible to get the optimal regularization matrix in the general case. So why it is impossible? Because MP tilde Q bar depends on MP tilde, and MP tilde solves a polynomial of degree above 5, which is probably impossible in the general case. We don't have an explicit formula for MP tilde of -1. Actually, MP tilde of z for any z in the general case, right? If you assume a finite, like say 2 or 3 eigenvalues, then you could solve it. But in the general case, the solution, we can't have a solution. But this expression can be solved numerically, right? So everything can be solved numerically using any optimizer. And the rho tilde here is defined recursively on the other rho tilde. So this expression is very non-trivial, but this provides the exact expression to the behavior using any diagonal regularization matrix. So hard, yeah, it is hard. But we want to draw some conclusions. So what we do in our work, we find a first case where isotropic regularization fails completely actually. So let's talk about this. Theoretically, it's not hard to make isotropic regularization fail. For instance, Zhao has shown that once you fix two indices, two eigenvalues, in the first task, the one will be fixed, and the second one will go to 0. In the second task, you have the exact opposite. The first one goes to 0, and the second one remains fixed. In this case, isotropic regularization fails. But we can't use this theorem because we assume that we have isotropic covariance matrix. So we show that even with isotropic covariance matrix, it fails. So assume that we are in the overparameterized regime. If we are not in the overparameterized regime, then reach can be reduced up to 0 loss because we are invertible, right? we are in a single task with no noise, so this is a very simple case. So let W star not equal to 0. If W star equals to 0, since the initial predictor is also 0, then using lambda goes to infinity, we can reduce the expected value of G1 ridge to 0, once again, because we basically stay in the same predictor. So it is case sparse with support S. S is the subset of the indices in which W star is not 0, and XS is the metric sub-index to those columns. We assume it has full column rank. Then after a single task with no noise, the ridge completely fails compared to the diagonal regularization matrix. So how do we show it? It will be a bit informal, but we show that ridge has a noise floor because it can be exactly from those conditions. It can't be solved. It can be solved up to 0 loss. And the generalized delta regularization, what we do is to construct a matrix in which the entries of the subset of S, we solve it up to 0 loss. Yeah, we can do it since X is a full rank column, and the other entries will go to infinity since W0 is 0. Right, so even in a very simple case, and also the assumption that X has a full rank column holds almost surely for any continuous distribution if K is much less than D, for instance, because you need to have linearly independent columns, K. So when does it succeed? So we derive not the sufficient conditions, but also the necessary conditions in order to the isotropic regularization to succeed. So there exists an optimal matrix of the form M star equals to lambda times identity for some lambda greater than 0, if and only if the covariance of W star is proportional to identity. Right, so if the covariance of W star is not proportional to identity, then M star will not be lambda times identity. And if the M star is not lambda times identity, then necessarily the covariance of W star is not proportional to identity if we have a unique minimizer. So once again, we verify empirically. Here we consider the linear case, but we construct the teacher region. So we consider two types of teachers. The first one is isotropic, where all the coordinates are equal to 1. The second one is sparse, where first 100 coordinates are equal to 1, the rest are 0. And we find that diagonal regularization metrics outperform significantly all the isotropic regularization matrices. And in the second case of the isotropic teacher, the diagonal regularization matrix is inferior to the regularization matrix. Actually, in the general case, we would expect the diagonal to be at least as good as isotropic case, right? But since it's MNIST data and it doesn't follow our statistical assumption, we would expect to the diagonal to not necessarily be the best. But even if we consider MNIST data, the diagonal regularization can provide us insight, the correct expected generalization loss can provide us insight into how choosing those diagonal regularization matrices. And by the way, we choose the diagonal regularization matrices by the real expected value, and we minimize it using some optimizer. Right, we know the teachers, so we can basically say what is the objective and solve numerically all the values. So summary, we find that exact generalization analysis can provide us insights into how choosing the regularization parameters and the step size and the number of steps, and also in some cases the regularization matrices. Optimal regularization scales as T over ln T in a pretty simplified linear setting. Relaxing the i.i.d teacher can provide us very different results. Gamma star scales as ln T over nt. While we assume a pretty simplified setting, our entire analysis was supported by experiments when our assumptions, of course, do not hold. And even in a neural networks model, for future work, one may consider non-isotropic covariance metrics. I'm not very positive about this direction, since once again, you would have to solve polynomials of degree above 5 in the general case. And analyzing nonlinear models, I actually know only one work that analyzed it in a single task case, and only the first gradient step. It might be interesting. They actually also simplified the real model, but it might be interesting to see how it cumulates between tasks. So maybe for future work.